I just bought ChatGPT Pro for $200, so you don't have to. So if you look here, the main reason I bought this thing is because I want to try out this deep research topic or this deep research feature. Yeah, it cost me $200, but I think this is gonna be worth it. I don't know. We'll see. I have a bunch of ideas of things I want to deep research, and I'm gonna drop videos on all of them, and then literally just drop down in the comments if there's specific things that you want me to deep research. I have a quota, so I can't just spam them, but yeah, these are the things that I want to use deep research for right now, and kind of see how it works. I think everyone else in this channel might be interested in these topics too. So I'm going to get a deep research in Python, current state of Python in 2025. I want to get a deep research into data structures and algorithms in 2025. I want to deep research into landing your first internship in software engineering in 2025 as well, because I know a lot of people here are students. So deep research on most relevant systems, system design concepts. I'm diving a lot deeper into infrastructure, so I want to do some deep research in infrastructure and infrastructure as code, and then some other product, full stack things like deep researching into Django, deep researching into React, deep researching into AI agents. I want to deep research into math, maybe deep research into growing my YouTube channel, and then deep researching into everything I need to know about AWS. So I think, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are 11 that I have, and I'm gonna drop you're gonna, if you see video videos like deep research in Python or deep research in data structure algorithms, this is where it's coming from. I'm just running it through this AI and seeing how this AI works. So yeah, this is February 15, 2025. So if you're watching this 100 years from now and you're looking at this thing like, wow, that's crazy, or you're probably like, yo, that thing sucks. It's a cool thought experiment. Hopefully YouTube never takes this down, and hopefully YouTube never goes down. So what is deep research? I think the first thing I want to do a deep research into data structures and algorithms, because a lot of my content is on that, and I know y'all love that. So let's just quickly talk about what even is deep research. So deep research, this was just launched 2 weeks ago, but it's an agent that uses reasoning to synthesize large amounts of online information and complete multi-step research for you. So it's a bit different. If you try GPT, the reasoning models, you would see that it takes some time to think. But this deep research, it will spend way more time thinking. It could spend 5 to 30 minutes of its time thinking about a problem. And it and like O1 and stuff doesn't really have access to the tools and scraping the web, but this deep research will actually click into different links and research it the same way that you would do your research if you're researching, right? If you're Google researching. So you click into different links, synthesize all that information, and it's gonna think for 5 to 30 minutes. So this is gonna be really interesting. I mean, y'all probably just want to see it in action. Let's just use it, and then we'll play. Let's skim this, and then let's figure out, just so we make sure we're not like using it wrong. So today we're launching deep research in ChatGPT, a new agentic capability that conducts multi-step research on the internet for complex tasks. It accomplishes in 10 minutes what would take a human many hours. Wow. Deep Research is OpenAI's next agent that can do work for you independently. You give it a prompt, and ChatGPT will find, analyze, and synthesize hundreds of online sources to create a comprehensive report at a level of a research analyst. Powered by a version of the upcoming OpenAI O3 model that's optimized for web browsing and data analysis, it leverages reasoning to search, interpret, and analyze massive amounts of text, images, and PDFs on the internet, pivoting as needed in reaction to information it encounters. This is sick. Because now it's getting up-to-date information. So when I ask it to research data structures and algorithms, it's going to also maybe teach me of things that are maybe on the horizon. I'm going to ask for that. The ability to synthesize knowledge is a prerequisite for creating new knowledge. For this, using deep research marks a significant step towards our broader goal of developing AGI, which we have long envisioned as capable of producing they're taking these LLMs to the extreme. You would never think an LLM could actually do AGI, could actually be AGI, but they're really pushing this. And Sam Altman really believes that with the current architectures we have, we could actually hit AGI. This is going to be a longer video because I'm going to let this GPT literally run for this whole question, deep research into data structures and algorithm. So, how to use deep research. In ChatGPT, select deep research in the message composer and enter your query. Tell ChatGPT what you need, whether it's competitive analysis on streaming platforms or a personalized report on the best commuter bike. You can attach files or spreadsheets to add context to your question. Once it starts running, a sidebar appears with a summary of the steps taken. Okay, we can see that it's thinking. Deep research may take anywhere from 5 to 30 minutes to complete its work, taking the time needed to dive deep into the web. In the meantime, you can step away or work on other tasks. You'll get a notification once the research is complete. The final output arrives as a report within the chat. In the next few weeks, we'll also be adding embedded images, data visualizations, and other analytical outputs. This is going to be sick. I like this. I actually like this feature. It's very expensive though. Compared to deep research, GPT 4.0 is for real time. Yeah. Deep research is more just like you're a manager. You want to talk to somebody and you just give them the task. They run out and do it, and then they come back with a detailed report. I really like that. Okay. So for business, look at this report. You could do needle in a haystack. Wow. You could do medical research, UX design. Oh, maybe I might need this for my UX design. Maybe for some of my other projects. Why would you deep research on an NFL player like that? It's a waste of money. So deep research was trained using end-to-end reinforcement learning on hard browsing and reasoning tasks across a range of domains. Through that training, it learned to plan and execute a multi-step trajectory to find the data it needs. It learns to backtrack and react to real-time information where necessary. The model is also able to browse files, graphs. Yeah, it goes crazy. Humanities last exam, like showing all the different, most of these research papers, they're just gonna talk about it, then start showing it across various benchmarks. OpenAI deep research. I've watched both of these videos already, so let's just get like a quick preview.
So you start up with a question and you might not know anything about it. And then you put your researcher's hat on and you're like, let me think about this a bit more. Where can I go look? Well, my name is Reem Anshasi. I am a director in the Research and Data Services Department in Bain, San Francisco. Good research, to me...
That's the Salesforce Tower 100%. Wow, that's a beautiful view. Yeah, that's the Salesforce Tower 100%. That's beautiful. That is crazy. I need to get... Whoever works at Oh, I know someone who works at Salesforce. I'm getting up there 100%. I'm getting a tour.
In Bain, San Francisco. Good research, to me, is being able to deliver the latest data, the most credible data. It's difficult because the research...
Okay, whatever. Okay, let's get into what we're going to do. We're going to do deep research on data structures and algorithms. I want you to perform deep research on the topic of data structures and algorithms. I want you to give me the most up-to-date information on relevant DSA topics specifically for, let's say, intermediate level. Wait, let's just let the AI guide us. I want to perform deep research on the topic of data structures and algorithms. Let's see. See, okay, it's guiding us. Fundamentals. Wow, okay, it's breaking. Since I want this to be beginner friendly, we're gonna go into the fundamentals and basics. Let's see if it's gonna deep research or just ask. Oh, okay. Arrays, linked lists, taxes, trees, graphs. Sick. Okay, now starting its research. I'll send this deep research report. I'll put this deep research report on my GitHub or something and have anyone who wants it get access to it. I want to see what you're thinking, brother. What do you see? I thought it said you're supposed to see. Okay, at the same time, let's look more into. Let's read that research. Okay. It's thinking. So it's fundamentals and basics of data structures and algorithms. I'm gathering insights on data and practical applications, ensuring beginner-friendly format, citations for accuracy, search. Animal rescue? What? Okay. This is sick. They need to make this side bigger. Have to spec the element there. Wait, let's change the wrong thing. Okay. I need to reduce this side. Bro, I just want to expand this. Okay. Okay. Let me figure out how to do that. Okay. How is this thing set up? Okay, we have this. I just need to reduce the width of this thing. Like this whole component on the side here. Want this whole. Yeah, how to reduce this width? This thing still doesn't expand. Uh-oh. Now I have this ugly UI. Flex full. Okay, still deep researching. Okay, whatever. So, let me just center this for y'all. So, they're piecing together what a data structure is. And it says its role is in organizing and storing data for efficient access. So this leads me to consider the linear versus non-linear classification of data. Okay, let me see. So Wikipedia's general sense covers linear and non-linear topics, but they might overlook category distinctions. Progressing through the coverage might inspire a clear understanding. So it's pulling in more data, like Scipulern. I discovered a section on graphs and need to scroll it. I'm simplifying linear data structures. So it looks like when it starts thinking about data structures and algorithms, it starts thinking about first what is a data structure, and now it's comparing linear data structures versus non-linear data structures. Arrays are static. Okay, what else to say? I'm simplifying linear data structures are sequential in one level, while nonlinear are hierarchical, and network-like static structures have fixed memory dynamics. Okay. It's interesting to see that mentions dynamic concepts but lacks specifics on static dynamics. You might need to deepen this distinction to, okay. Going on Stack Overflow. So arrays are static while other memory structures are dynamic, capable of growth or shrinkage. Okay. I'm gathering static versus dynamic data. Okay. Scipulern looks cool. Did it finish? Oh, it's still going. Let me center this again for y'all. An algorithm involves a step-by-step process or set of instructions to complete a task, often by computer. Okay, now it's trying to figure out what an algorithm is. It dug into data structures, but at a high level, what are the data structures and what are the different forms, like linear versus non-linear, static versus dynamic data structures. That's an interesting way to look at it. Now it's trying to dive deep into what's an algorithm. So it's saying an algorithm is a step-by-step process or set of instructions to complete a task, often by computer, and can be formally defined and analyzed for algorithm complexity. Examining the inclusion of big O notation. So an algorithm is just a step-by-step process or instructions of things to do. And it's usually done by computer. And you can analyze the time or the complexity of the algorithm. That's a pretty neat way of looking at it. Now they're gathering info of explaining Big O to beginners. They went on free code camp. So they're just scrolling the web. Okay, let's break down the definition of time and let's break down the definition of time complexity and how it uses Big O notation to outline worst case scenarios and input size scaling. So now it's talking about how Big O is all about the input size and how it scales based on the input size. I'm curious about using space complexity data camp as a search term. This could help tailor the learning. Okay, it's looking at unstop. How long has this thing been going? I think at least 10 minutes. Big O notation evaluates an algorithm's worst case time complexity. It differentiates best case, worst case, and average case. Yeah, this is like intro to data structures and algorithms stuff you learn. So Geeks for Geeks, yeah, I like that website. So it's interesting how this thing is pretty much looking at the same websites that I'm looking at. Maybe it's because it's just trained on other software engineers, so it's kind of thinking like us too. BFS for DFS. So more DFS and BFS. DFS heads deep into each branch, then backtracks. BFS explores all neighbors at each depth level. Yep. I'm evaluating the amount of content on focusing on. Wow, this thing is looking through so many websites. This is actually interesting. Like, it already has 51 sources. So now it's getting deep into the different data structures. So arrays. Singly linked list, doubly linked list, and circular linked lists. Currently, I'm figuring out how to describe linked lists, stacks, and queues. It's interesting to see the benefits of linked lists, like data insertion challenges, and when it's streamlined. Wow, this thing is gonna pump out like 20 different YouTube video ideas for me. This actually might be worth it. Dude, wow, this thing is crazy. I don't know though. I'm just like talking before I even seen the report. We're gonna see how good the report is. I'm analyzing stack and cube operations, hashing techniques. So now they're diving a bit deeper into hash maps. Quick lookups. This approach underscores efficiency. So yeah, it's going into hash maps a bit. So they're detailing separate chaining and open addressing reference. They're looking at PDFs. Wow, this is good. This is like, just looking at this report, I'm just getting so much breadth, and I'm just recalling all the stuff that I learned in college, which is actually just insane. Maybe I'm gonna get it to deep research into a college degree, like what we should teach for, or like how to structure a college degree for computer science in 2025, and then have our thoughts on it. Because I think the education system is a bit broken. So they're detailing collision resolution and discussing binary trees, BSTs, heaps, and tries. So these are just what we need to know. These are just like table stakes things if you're applying for FANG companies. So they're strategizing on how to present heaps, specifically binary heaps, and their critical properties and applications. They're reading this article, and they're figuring out max heaps, min heaps, highlighting heap properties like parent-child order. Okay, cool. I'm digging into terms like adjacency matrices, adjacency lists, and graphs, traversal methods such as DFS and BFS. This is sick, man. Dijkstra's algorithm, Floyd Warshall's. Okay, I actually don't know much about Floyd Warshaw's algorithm, so I think I'm gonna learn a lot from this. Prims. Yeah, I've done prims before. So now they're clarifying data structure categories like linear versus nonlinear, static versus dynamic, and listing examples such as arrays and linked list. I think that's a good video topic on its own. Okay, now it's diving into things like greedy algorithms. Looking for divide and conquer. These are the divide and conquer. I need to practice more on those algorithms and coming up with those. Those I didn't practice those as much because they're not really asked, but I think they're interesting ways to solve problems because when you're working with large scale data, you need to divide that data and like run them on different machines. So recursively simplify complex dynamic programming, backtracking. So it's looking at W3. So it's looking to bubble sort, comparing and swapping. Piecing together selection sort. Identify its method of repeated minimum element identification from an unsorted array to form a sorted array. Okay, it's talking about selection sort, merge sort, quick sort, linear search, binary search. They're outlining a progression of complexity classes. And having been doing a lot of research in this area for the last few months and coming up with all these videos, I can probably confirm here that this is pretty much what you need to know in order to land a job at Fang. Like this is analyzing everything you need to know to land a job at Fang, and it's doing a really good job at it. It's still researching though. Go on Chegg, OpenStax. So it's talking about real world examples of data structures and algorithms like B trees, databases, Bing search, covering data structures, algorithms, and BFS. Planning to include relevant citations and a few concise code snippets. I'm demonstrating stack, push, pop, and Q, NQ, DQ in Python to illustrate these structured operations. Mentioning Python's DQ for Q. Wow. So I'm thinking about divide and conquer problems, which breaks down problems into smaller, simpler subproblems for recursive solution, leading to me to consider its effectiveness. I'm mapping out how dynamic programming breaks down problems into simpler subproblems and solves each one uniquely. Now it's mapping out if we should combine or separate stacks and queues. Trees will be detailed with binary tree, BST, heaps, and tries. Okay, I did videos on all of these. Kind of. Maybe not binary search trees. So for graphs, an overview of vertices, edges, plus DFS. Common algorithms will cover sorting. I like this a lot more. This is, dude. I might be giving GPT. I've already given GPT like $1,000 this year. Maybe I'll try. Google's deep research. Why is it still thinking? So I'm breaking down key terms like big O notation, complexity analysis, and practical applications of data structures in database compilers and networking. This involves categorizing different sorting techniques. I'm ensuring accurate citation formatting, focusing on practical usage. Honestly, I really like using GPT more than going to school. I learned so much from just asking it questions and just learning through here. I wonder if there's gonna be like people are gonna be self studying in the future and never having a teacher. Okay, it's talking about bee trees. These are more practical stuff. Wow. Now it's getting deeper. So now it got a pretty much a breadth of everything, all the different topics, and now it's trying to figure out when this is actually used in the real world. Because I know a lot of people are like, oh, this is never used in the real world. But now it's going to do that research. So it's organizing the blog. Now it's okay. Now it's now what is it getting back into? Okay. Now you kind of see how it's going. I'm gonna pause it here and I'm gonna check in when it's done. I'll be right back. I was on mute. Okay, so it finally finished its deep research and it took about 10 minutes across 51 different sources. So it was more than I would have ever done. It synthesized all that information, dropped the links to all those sources so we can click into them if we want to. But let's get into it. So, so this is fundamentals and basics. So what introduction to data structures. So definition and importance. In computer science, a data structure is a way of organizing and storing data in memory so it can be accessed and modified efficiently. Data structures define the layout of data, how the data is stored, and operations that can be performed on the data. Choosing the right data structure is crucial because it can greatly improve the performance of software. Efficient data structures enable programs to manage large amounts of data, such as databases, search indexes, and are key to designing efficient algorithms. Okay, it's just introducing what is a data structure, and it's kind of the same way I described it in my videos as well. I have a video of what is a data structure. Maybe I'll redo it, but so in real world applications, different structures are used for different purposes. So for relational databases, B trees are used a lot. I should dive deep into B trees because everyone needs to know what a B tree is. It powers lots of databases, lots of SQL databases specifically, especially indexes. Compilers. I need to dive deeper into compilers. I never took a compilers class, but I'm gonna do a deep research on compilers. And just learn all of those. Dude, this is fun. You're gonna learn a lot this year in 2025. We're gonna spam learning content and just we're already a month and 15 days in, and how much stuff have we learned together as a YouTube family? And I'm studying stuff every single day with y'all too. So we're gonna be dropping content every single day, learning new topics every single day. We're literally gonna go crazy. So what are we? Categories of data structures. So there's linear and nonlinear data structure. So in a linear data structure, elements form a sequence or line. Each item is adjacent to the next. So these are arrays, linked lists, stacks, and queues. These are linear data structures. Non-linear data structures are elements that are more hierarchical or network fashioned with no linear sequence. So these include trees and graphs. In linear data structure, there's typically a single level organization, whereas nonlinear organizes nodes in multiple levels. That makes sense. So there's also the concept of static versus dynamic data structures. So static data structures have a fixed size or capacity at the time of initialization. For example, an array is static and it cannot grow. You can turn it dynamic, and I talk about that as well. But when you're making it dynamic, you're essentially just creating a new array that's 2 times bigger than the last one, and then like copying over all of all of the elements in your smaller array into that bigger array. And now that big array, you can add more elements because you already created a new array that's double the size. What else? Static arrays have a fixed memory footprint, which simplifies memory management, but can be inefficient if the allocated space is underutilized or insufficient. A dynamic data structure, on the other hand, can grow or shrink as needed. So that includes linked lists and dynamic arrays. Dynamic structures use memory flexibly by allocating or deallocating memory in the fly. This makes much better use of memory for different data sizes. The trade-off is that dynamic structures manage memory at runtime, which adds complexity and potential overhead. And with dynamic memory, you can't just like randomly access in the middle of it, I'm pretty sure. Because like with static, you grab a contiguous space in memory and then you could easily access one. I'm going to dive deeper into C++ and managing memory on the computer. I'm going to go crazy on this deep research. There's so much topics that I just want to just go into after reading some of this. So common data structures includes arrays, linked lists, stacks, queues, trees, graphs, and hash tables. So everyone who's trying to break into Fang... Oh, what is this? Just gotta fix my green screen. Anyone who's trying to break into Fang and thinks that there's way too much things to learn, honestly, you just really need to know. The hardest part is pretty much getting an interview. And then after that, you really only need to know these basics: arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Each of these will be explored in detail in later sections. In brief, an array is a collection of elements stored contiguously. A linked list is a chain of nodes where each node points to the next node. A stack and queues are linear data structures with restricted access. So stacks and queues are essentially like arrays, but there's restricted operations you can perform on it. So for stacks, it's last in, first out, and then queues is first in, first out. A tree is a hierarchical structure of nodes, like a binary tree. A graph is like a network, so a network of nodes connected by edges, and a hash table. And a hash table uses key value pairs with hashing for fast lookups. These structures form the backbone of software development and efficient computation. I see so much people hating on LeetCode, but what they're trying to essentially just test you is on these fundamental data structures and algorithms. Yeah, I know some of the questions just are way too crazy these days, but I think that just comes from a little bit of inflation because people already know how to use LeetCode and they're spamming LeetCode. So there's a bit of inflation of how good you need to be at LeetCode in order to get a job. But I think at the end of the day, it probably started off with a good intent, which is just testing good data structures and algorithm knowledge. Maybe I'll talk about that in a different video, DSA inflation. Like I think there's been some inflation on how good people are getting, and now it's kind of getting unreal because everyone just has access. Okay, that was a high level on everything related to Okay, let's look at the sections. There's intro to data structures. Then there's intro into algorithms. Dude, this is a long... Okay, then it talks about... It goes into intros, then it dives deeper into it. What are the different common ones? Then it goes, deep into the different ones. Linked list, W linked list, circular linked list. stacks, queues, hash tables, trees. So when it gets into trees, it breaks down into a bunch of other tree related things, such as binary trees, binary search trees, heaps, prefix trees. Talks about use cases, which are good. Then it talks different tree traversals, graphs, so different ways of representing graphs, different traversals, shortest path algorithm. I need to learn Floyd-Warshall's algorithm. Topological sort, graph search, network flow algorithms. Wow, just getting... I need to learn all... I want to start learning all the math needed for competitive programming too. So I want to actually... I might use deep research to help me get into there. And this, honestly, 2025 is the year of knowledge building. I want to come out this year with so much more knowledge than I had in 2024. And then for 2026, you're just going to see me delivering on stuff. I think that might have changed from what I said before. But this is just... I'm just getting hyper right now learning about this stuff. So, okay, just talked about the different algorithms or dive deeper into different data structures. Now it's going to go deeper into some of the common algorithms, such as bubble sort, selection sort, insertion sort, merge sort, quick sort, and other sorts. Dude, this is a lot of information. So searching algorithms like a linear search, binary search, hash table lookup, recursion based. Okay, it talks about recursion. Okay, this report's gonna take me so long to read. It's actually pretty long. So it talks about recursion basics. I think it's covering good topics. I'm gonna literally just skim this. So we have a base case. So then we have graph algorithms. Graphs are rich. Okay, I'm kind of interested in this. Shortest path and minimum spanning trees. This is a classic algorithm for finding the shortest path from a single source to all other vertices in a weighted graph. Non-negative edge weights. That's important. Relaxes all. Updating neighbors if a distance. Okay, what does it mean by relaxing? I remember that a little bit. Because I think that's a very important part of the algorithm, relaxing. So I need to explain that. So it's widely used for GPS. It doesn't work for negative weights. So if we want to do negative weights, use Bellman-Ford or Johnson's algorithm. Okay, what is Floyd-Warshall's algorithm? This computes the shortest path between all pairs of vertices. Interesting. It handles positive or negative weights, but no negative cycles. What the heck? Okay, I need to learn Floyd-Warshall's algorithm. I wonder how much this is actually used. All pairs short. It could be used to analyze all pairs, shortest routes. Okay, prims. Don't you need to use union find for this? Wait. Oh no, you use union find for Kurzweil's algorithm. Okay, minimum spanning tree makes. I need to research these again. It's literally been like 4 years since I got out of college and learned these, but I'm down to learn it again. So Kurzweil's algorithm for minimum spanning tree uses union find. I'm gonna now I need to know that I need to. The good thing about this deep research is then you get to understand what you don't know, and then dive deep into it. So yeah, I think that's the important thing in life in general, or in software is you might think you know everything, but there's probably you're just overlooking some things. So if you get somebody to literally search the internet and show you their version of a topic, you're gonna find things you don't know, and then you just look into those and just expand your horizons. So I'm just realizing I don't really know Floyd Warshaw's. I forgot what relaxing is. I need to touch up on Crimson Crystals, Primson Crystals. A-star algorithm, topological, Tarjans. Okay. I need to do a deep dive into dynamic programming from literally zero to hero. Dude, I have so much videos ideas. It's crazy. So now, okay, just talked about a ton of different algorithms. I think this is good. If I spend about like a month learning these, I'll be primed. And I'll record it all for y'all, and y'all will all learn this stuff too. But I want to do more research on some practical stuff, so maybe I won't go completely deep into this. I'm going to do more deep research on some of these things that I was thinking about here. And yeah, I'll probably use deep research to build me a full report, and then just use a regular chat GPT to fill in some of the details. So, okay. What are the different algorithm complexities recap? Constant time, array access by index. And then we have logarithmic time, binary search, operations on balanced BSTs, O of n, linears like scanning, n log n, sorting algorithms like merge sort, heap sort, O of n squared, which is very simple sorting, and naive double loop algorithms. Exponential is just like backtracking combinatorial problems. Dude, I'm getting just so much refreshers from university days. The difference in growth are dynamic. For instance, the O of n algorithm on input side of 1000 might do an order of 1 e to the 6, whereas O of n would do e to 12 operations, which is a million times more likely, and likely infeasible. So the difference between O of n and O of n squared is pretty much night and day, it's saying. That's crazy. So if you're in an interview and you are talking about your O of n squared algorithm, you're defending it really hard. Like the difference between O of n and O of n squared seems like it's night and day. I didn't even realize that. A log of n operation on 1 million elements might do about 20 operations. Might do roughly O of 20 e to 6, which is fine, whereas O of 2n is completely impossible. And this is why understanding big O is crucial. It'll let us foresee how an approach will scale. As a concrete example, a sequential search algorithm grows linearly, doubling the input size roughly doubles the work, but an exponential algorithm grows so fast that even slightly larger inputs becomes impossible to handle. As noted in theory, no amount of hardware improvement can save an inherently exponential algorithm for large n, whereas an efficient algorithm will eventually outperform a less efficient one as n grows. For instance, an O of n algorithm will remain practical as n scales, but a 2 of n algorithm quickly becomes impractical if n. This is really important stuff, and I actually like every people complain about having to learn DSA, but this stuff is very critical for working on hard things. Always aim for the lowest complexity algorithms in terms of big N for the problem. Often this is achieved by using appropriate data structures and algorithmic techniques. So now it's diving a bit deeper into big O and complexity. Space and time. What else? Dude, this is a comprehensive. Okay, it talks about practical approaches and then it's done. Okay, let's finish this practical approaches. So, what are the practical applications of data structures and algorithms? So let's connect these concepts to some practical applications and scenarios in software development. So databases. Data structures and algorithms are heavily used in database systems. For example, most relational databases use B tree or B plus trees data structures to index data on disk for efficient retrieval. When you query a database for entries with a certain key, the B tree index, a self-balancing search tree, allows the database to find the results in log n instead of scanning every record. Hash tables are also used in databases for hash indexes or in memory for join operations. Query optimizers use algorithms to determine the best way to execute a query. Operating systems. The OS uses data structures. Okay, it's used a lot in OS. Like, it uses linked lists and queues and trees all over. So, okay, the job schedule is a priority queue to process CPU time. Memory management uses linked lists or trees to keep track of free memory blocks. File systems use B trees to index files and directories on disk. Even device drivers and networking code use ring buffers, circular queues for buffering data. I see. Data structures and algorithms are everywhere. Okay, networks are naturally modeled as graphs. But the thing is, there's only a small portion of people actually implementing in this stuff, and it's abstracted away from a lot of engineers. So that's why a lot of engineers don't even think it's useful to know. Even device drivers and networking code. Okay. Networking graph. Networks are naturally modeled as graphs. Routing protocols use Dijkstra's and compute shortest paths for routing tables. Social networks and recommendation systems use graph algorithms to find connections or similar users. Web search engine models the web as huge okay. Encryption security. Dude, this computer science field has so much breadth. It's insane. It's grown like crazy in the last 50 years. There's so much to learn. All of these things, a lot of people won't really have to dive deep in this. They'll be working on product related stuff, so you don't really have to dive deep into a database or operating system, but use it day to day. But then you could also dive deep into these if you wanted to and be a complete domain expert, which is crazy. Honestly, I prefer just having a breadth over everything and just kind of indexing it in my head. And just this stuff is still important to me, but I'll probably will never go deep into it, and I'll mostly only care about building products for people. Algorithms are key, not just data structures, but understanding complexity is vital. For instance, so encryption and security. Since cryptography, okay, talks about cryptography, artificial intelligence. While high level, these fields use core data structures and algorithms extensively. For example, decision tree classifiers use tree data structures. Neural networks use efficient matrix algorithms, which which rely on this. Graph algorithms are used in things like knowledge graphs. Dude, at some point I want to apply to masters. I want to try to get into like an Ivy League school. So maybe I'll use this to craft my resume for getting into one of these Ivy League schools, because that would be a crazy thing. A compiler uses numerous data structures. It often builds. Okay, I need to dive deeper into compilers. Okay, web development. When is this used in web development? Even high level web programming benefits from knowing these fundamentals. For example, using a library framework, understanding that a certain operation might be O of n versus O of 1 can explain performance issues if you handle large JSON data. Using a proper data structure, maybe indexing it with a hash map for quick lookups could be needed. Maybe many backends involve caching. Yeah, even as a web developer, you kind of need to know these, but not on the same level as if you're working on databases or if you're working on compilers, if you're working on networks, if you're working on operating systems. Coding interviews, everybody's favorite. So from a career perspective, knowledge of data structures and algorithms is tested in technical interviews for software engineering roles. Interviewers often ask candidates to solve problems that involve choosing appropriate data structures and writing efficient algorithms under time constraints. For example, you might be asked to design an algorithm to merge k-sorted lists or to find the longest substring without repeating characters. They assume familiar. So yeah, they make you implement algorithms, and they don't test you on the specific data structures and algorithms, but you definitely have to. But you will have to use the data structures and algorithms under like to solve the problem. So it's not like they're gonna be like, oh, implement an array, implement a linked list. Some do, but not. That's not always the case. So competitive programming contests rely on these concepts. So real world optimization. So cool. So in summary, data structures and algorithms are not just academic, they manifest in every software system in some form. Efficient code often boils down to using the right data structure to get a good complexity and the right algorithmic approach. Understanding these basics provides a toolkit for reasoning about and improving code. It helps a developer think, could this operation become a bottleneck? What's the complexity? Is there a better way to structure the data? These questions are critical in in engineering high performance scalable software. Yeah, whether it's implementing a feature, you're debugging a slow program, acing a coding interview, or designing a large system, a solid grasp of data structures and algorithms is invaluable. By learning these fundamentals, arrays, linked lists, stacks, queues, hash tables, trees, graphs, and the algorithms that act on them, one is well equipped to tackle a wider range of computational problems efficiently. It's the foundation upon which more specialized and advanced computer science knowledge is built. Wow. Okay, we just did an hour of diving deep into data structure and algorithm. This video is going to be called Deep Research in Data Structures and Algorithms. I heard that the YouTube algorithm really prefers videos that hit exactly the 1 hour mark. And right now we're at we're at 59 minutes and 50 seconds. So I'm going to close this right at the hour mark and stop recording. But I hope y'all have a good rest of the day. 3, 2, 1.